Hello and welcome to this video where we're going to be deriving the Taylor series. So, the Taylor series is as follows. If we have a function f of x, then if this function is valid, which we will talk about later, then when a is some element of the real numbers, we can have that the function f of x is equal to the infinite sum as r goes from 0 up to infinity of x minus a to the power of r divided by r factorial times f r of a, where fr is representing the rth derivative of f. So that means you take the derivative of f r number of times and then to that value you substitute a. If we have that and we sum all of these expressions together, then f of x is going to be equal to that sum. So here we have the condition that f of x should be some valid function. What is a valid function? Well, let's go down here and talk about it. Some valid functions that work are e to the power of x and tan inverse x. Here we can see e to the power of x has a Taylor series which makes it easier to calculate. Taylor series convert complicated functions into simple integer power of x functions like such. E to the power of x is equal to 1 plus x squared over 2 factorial plus x cubed over 3 factorial plus x to the power of 4 over 4 factorial plus x to the power of 5 over 5 factorial and so on. This is the Taylor series of e to the power of x. Similarly, tan inverse x has a Taylor series as follows. Tan inverse x is equal to x minus x cubed over 3 plus x to the 5th over 5 minus x to the 7th over 7 plus x to the 9th over 9 minus x to the 11th over 11 and so on. This is the Taylor series of tan inverse x. So then, these are valid functions. What makes these functions valid? Well, they need to satisfy these two conditions here. The first condition for a function f of x to be valid and follow the Taylor series summation is if the function has an infinite differentiability, meaning we can take as many derivatives as we want and not run into any issues. So here the first condition is that the function must be infinitely differentiable. We can differentiate it once and get f prime of x as in the first derivative. We can take f prime of x and differentiate it to get the second derivative, which is f double prime of x. We can then take that derivative again to get f triple prime of x, and we can keep going and take as many derivatives as we want. The second condition that needs to be valid is that for this term here, which we're going to call r sub n of x, it is the remainder value which we're going to find out as we derive the Taylor series. For now, we just call it r sub n of x. If r sub n of x is equal to this value here, 1 divided by n factorial times the integral from a up to x of f to the n plus 1, as in the f's n plus 1 derivative evaluated at t, times x minus t to the power of n integrated with respect to t. If r of r sub n of x is this expression here, then we must have the condition that the limit as n approaches infinity of r sub n of x is equal to 0. We will see why this is important. This is important because otherwise the Taylor series does not converge to the exact value we want. So then we will have to have the condition that this limit is approaching 0. Given that condition, we can say that we can form a valid Taylor series for the function f of x. Further, there is another condition that says that the function needs to be analytic. I have merged that condition into here and said that this first condition needs to be met for all x in some finite interval around a, meaning not just the value equal to a, but rather some other values around a, which we need to also have this condition to be valid. If we have r sub n of x valid, as in its limit as n approaches infinity approaches 0 for some valid range around a, and f of x is infinitely differentiable, given these two conditions, then f of x will have a Taylor series expansion that will be like this. F of x will be equal to the sum as r goes from 0 up to infinity of x minus a to the power of r divided by r factorial times the rth derivative of f evaluated at a. So then, let's go and try to prove that this Taylor series is in fact this expression here, and that we can find it and we can equate the left hand side and right hand side. So let's go. Before starting the proof, we first need to establish two lemmas and prove them and continue. Lemmas are basically proof that we do before our actual proof that we are going to be using within our proof. The first lemma we are going to be using is related to integration, and the second lemma is also related to integration, but the first one is more basic. It is using the fundamental theorem of calculus. If you don't know about calculus, click this video over here. If you don't know about integration, click this video over here. So then, moving forward, the fundamental theorem of calculus can be used to find that the integral from a to b of some function f prime of x, which is the derivative of another function which is f of x, integrated with respect to dx, as in with respect to x, is equal to that function f evaluated at b minus that function f evaluated at a. We have this thing. This is coming from the fundamental theorem of calculus. We are going to be using this thing to derive our first lemma. So for our first lemma, what we are going to be doing is considering the integral from a up to some value which I am going to be labeling as t0. I'll explain why the t0 is, and you'll also understand it's because of the way that I'm doing the proof. These symbols are going to be intuitive and useful. So the integral from a to t0 of f prime of the variable which I'm going to call t1 dt1. So we are going to integrate f prime of t1 with respect to t1 as t1 goes from a up to t0. This is going to be equal to, according to our fundamental theorem of calculus, it's going to be equal to f of t0 minus f of a. Rearranging this expression, taking this f of a to the left hand side, we are going to get f of t0 being equal to f of a plus the integral from a to t0 of f prime of t1 dt1. Now then, this is going to be one of our first equations that we're going to be using, and we're going to be using this and a family of equations like it. Considering instead of this, if we consider the derivative of f dash t1, the integral of the derivative of f dash t1 or f prime t1 is going to be f double prime t, and I'm going to put a different variable here. I'm going to put t2. You'll see why I'm doing this, why I'm putting these kinds of variables rather than putting some random name like, let's say, x or u or something. I'm going to be doing this because it's systematic. If we consider this thing's integral from a up to t1, this is going to be this function's integral, as in the function whose derivative is this function, as in f prime evaluated at the top limit, which is t1, minus the bottom limit, which is going to be a, so minus f prime of a. So then, given this, we can rearrange this and say that f prime of t1 is going to be equal to f prime of a plus the integral from a up to t1 of f double prime of t2 dt2. You'll notice the symmetry of this expression that we just got with the above expression. In fact, they are exactly identical. It's just that now we have a different function as our main function and its derivative inside of the integral. So we can see here, we have over here some function f, its derivative in the integral, and it evaluated at a here. Here we have that function's derivative, which itself is being treated like a function and taking its derivative into here. This is equation number 2. Moving on, we can do this more and more. We can continuously do this. Doing it one more time, we can take f double prime of t, which I'm actually going to put f double prime of t2. You'll see why we're doing this. F double prime of t2 would be f double prime of a plus the integral from a up to t2 of f double prime's derivative, which would be f triple prime. And f triple prime, I'm going to put the variable in here as t3, dt3. This is going to be equation 3. Moreover, as we keep doing this, we can see that any integral, which I'm going to be representing as fn of t, and here, since our zero derivative having a variable t0, we can see that the n derivative would be correspondingly having a variable tn. This is just so that we can make this systematic and make the equations look nice. You don't need to do it like this, it's just that I like doing it this way because it makes everything systematic. So then this would be equal to the n derivative of f evaluated at a plus the integral from a up to t sub n, as in the same exact variable that we have here. You can see that, of the value of the very next derivative, here we can see the second derivative has the third derivative in the integral, the first derivative has the second derivative in the integral, therefore the nth derivative would have the n plus 1 derivative in the integral, evaluated at t sub n plus 1 d t sub n plus 1. So that this is our formula, and here I'm going to label this as the n plus 1th equation here, because here the second equation is labeled number 2, the third equation is labeled number 3, and then the t sub n plus 1 would be labeled as the n plus 1th equation, and we have a bunch of equations in the middle here as well. All of these equations are valid under the fundamental theorem of calculus. This right here is going to be taken as lemma 1, so I'm going to put a star over here. Using this is going to be what I call lemma 1. Any nth derivative evaluated at any value is going to be that value evaluated some other value which we are going to be calling a, plus the integral from a up to our required value of that function's derivative. Here we have the first function f, its value at t0 is going to be its value at a, plus the integral from a to t0 of its derivative. Similarly, its derivative is going to be its derivative evaluated at a, plus the integral from a to the corresponding input value of its derivative, and so on. This is our first lemma. Our second lemma is going to be specifically regarding a certain integral. Integrals of the form I equal to the integral from, let's say, a to b of p minus x to the power of n dx. I want to do this one because we see it continuously when we are deriving the Taylor series, and I don't want to keep you substituting and showing you what the answer should be. So instead we're going to prove it for all possible values, and then we're going to take it as given. So here I'm going to have another condition for n not equal to -1, because at n equals -1 something else happens which we're not going to talk about during this video. So then for n not equal to -1, this integral here we can apply a u substitution and turn it into something else. This should be obvious to you, but we're going to do it from the base anyway. So if we let the u value that we're going to be substituting here be p minus x, then we can get that du should be, p is a constant in this context relative to x, so therefore its derivative is going to be 0, and negative x's derivative with respect to x is going to be negative dx. So we have negative dx. So du is equal to negative dx. Furthermore, considering the values, the limits here, we have a and we have b. At x equal to a, u is going to be equal to p minus the value of x, which is going to be p minus a. So u is going to be p minus a. Similarly, at x equal to b, then u is going to be the value of x, which is b, and then p minus b. So here we have u equal to p minus b, u equal to p minus b. So then using these new limits and this expression here, we can write that this integral I is also going to be equal to the integral from the lower value, which is going to be p minus a, to the upper value is going to be p minus b of, and then in here what we have is going to be u, which is here, to the power of n. So u to the power of n, since p minus x is equal to u, so therefore this thing is going to be u to the power of n, and dx needs to be replaced by -1 times du, because negative dx is du, therefore dx is negative du. So we have -1 times du. Now then, here, since we have this -1 here, we are going to swap these two limits of this integral here and turn this into the integral from p minus b to p minus a of u to the power of n du. Now then, what we are going to do here is take this thing and we are going to evaluate it. We know how to do u to the power of n with respect to u. This is going to be u to the power of n plus 1 divided by n plus 1 for the limits as we get p minus b up to p minus a. This is what we have to evaluate. So we are going to take this as a lemma and immediately take this thing when we need it in the future. So here all we have to do here to find the exact value is to substitute p minus a into here and p minus b into here and subtract the two. So basically what we have here is p minus a to the power of n plus 1 divided by n plus 1 minus p minus b to the power of n plus 1 divided by n plus 1. We are going to label this lemma 2 and we are going to be using it immediately without proving anything when we are solving our problem. So here we have lemma 2. I'm going to label it as lemma 2 and we are going to move to the actual derivation. So now that we're done with the lemmas, let's go to the actual derivation. The actual derivation goes like this. We are going to be taking this first lemma's first equation over here, saying that ft0 is going to be equal to this stuff on the right here. We're going to take it down. What we're going to do is into this equation, we're going to substitute the second equation. So here, in replacement of this f prime t1 over here, this f prime t1, we're going to be replacing this f prime t1 with the expression for f prime t1 that we had above. So here, going up, we're going to be replacing it with this expression on the right here. You can see this expression on the right here is what we're going to be replacing f prime t1 with. So I'm going to copy it. We're going to paste it as required. First off, we're going to rewrite everything else except that last part. So here we have this equal to f of a plus the integral as we get t1 going from a to t0 of f prime t1. As we saw above, f prime t1 is equal to this expression here. So we're going to substitute that in place of f prime t1. So then doing that, we have this expression now. What I'm going to do here to avoid confusion is color code some of these. I'm going to color code the fa in green. So this fa is going to be green. This is going to be green. This integral I'm going to color code in red. And as such, this is also going to be in red. So I'm going to label this first integral over here as being I1, and we're going to later label another integral as being I2. So we're going to label this I1 and move on. Now then, let's examine what we have here. Here we have an integral as t1 goes from a to t0 of f prime a, which is a constant, plus another second integral. So here what we need to do here is to take these two terms and separate them into two pieces. We're going to do this. Take this f prime a, take it separately, take this integral and take it separately. So what we're going to do is say this is equal to f of a plus, taking this term out, what we have is the integral from a to t0 of f prime a dt1 plus the integral from a to t0 as t1 changes of the second integral over here, which we are going to write as the first integral, the integral from a to t0 of the second integral from a to t1 of the value of f double prime of t2 as t2 changes as t1 changes. So this is the expression we have here. Over here, I'm going to now color code this differently. This thing of course is going to remain as green, but I'm now going to color code this part as, let's say, this magenta like color, and this other integral I'm going to color code in orange. This integral I'm going to label as I2. So this integral here, I'm going to take it and label it as I2, and now we're going to keep I2 separately and we're going to solve it later, and we're going to simplify this integral on the right here. So here, this purplish integral here, we're going to be simplifying it. Simplifying it down, what we have here is equal sign. We have fa and then plus this expression plus I2. So now, solving whatever this is here, we have f prime a inside, and since a is a constant relative to t1, f prime a is also going to be a constant. So here we have basically a constant on the inside of an integral. There's nothing else in here, it's all alone. We have f prime a dt1 going from a to t0. So therefore the integral here is going to be the constant f prime a times t1, where t1 goes with the limits from a up to t0. So we are varying t1 from a up to t0 and taking this integral, which means this is the expression we get. Over here, this expression is going to be t0 times f prime a minus a times f prime a. What I'm going to do is factorize out the f prime a and write this as t0 minus a times f prime of a. So writing it down like that, I'm going to say this is equal to, and over here what we have is f of a plus, simplifying this thing we have t0 minus a times f prime a plus I2. So here color coding this as I did previously. This thing is green, and then we have this part over here which is the purplish color, and we have another integral here, the orange integral, which we still need to solve. But here these first two terms, the green term and the purplish term, are now no longer being integrated. They are outside. We have fa and t0 minus a times f prime a. So therefore ft0 here, ft0 is equal to f of a plus t0 minus a times the derivative of f evaluated at a plus this other integral I2. Now then, we are going to take I2, solve it separately and then bring it back. Considering I2, we are going to write it down as I2 over here, I2 equal to, and we're going to rewrite it as this thing. Actually, we'll just copy paste it, it's easier. We just take this thing, Control C, take it down, Control V, change its color to blue and analyze what this is. So what I'm going to do here next is going to be something called changing the order of integration. In order to do this, I first need to consider what's actually happening here. So then, considering what's happening here, we can see there's a variable t1 and a variable t2. t1 is going from a up to t0, and as it goes like that, we have another variable t2 which is going from a up to that value of t1, as in the current value of t1, and then when that happens, we are evaluating what f double prime of t2 is, and then we're adding all of these values together. So then if I represent this on a graph like this, what we have is, if I write this as the t1 axis and the t2 axis, t1 is going from some initial value, let's say a, up to some final value of t0. So t1, we could say t1 is going like this, upward like this, and as t1 increases, t2 is increasing from a up to the current value of t1. So then when t1 is equal to a, t2 is going to be going from a up to a, because here at that point t1 is also going to be equal to a. However, once we get the final value of t1, as in t1 equal to t0, then over here we're going to have t0, and then t2 is going to be going from a up to t0. So therefore when t1 is equal to a, we're going to have t2 also going from a up to t0. So then along this thing, what's going to happen is, along this line here, which is the line of, if I can draw it correctly, this line here, which is the line of t1 equal to t2, along this line we are going to have t2 being its maximum value at this point. So t2 is going to have its maximum value at these points here. So here what's going to happen is, t1 is going to be changed to some value along the range from a to t0, and for some particular value of t1, t2 is going to be increasing from that value of a up to the corresponding value of t1. So this is what's going to happen. When t1 is this value over here, t2 is going to be varying from that value a up to here. When we have t1 equal to this value here, t2 is going to be varying down from a all the way up to this value here. So this is what's going to happen. t1 is going to be changing from a to t0, and for some particular value of t1, t2 is going to be changing from a up to t1's current value. So then basically we're adding up all the values of f double prime of t2 for all the possible inputs along this triangle here. You can select any point along this triangle. We're going to have a corresponding t1 and a corresponding t2. We're adding all of those values together and taking that as our final sum. So then here, if we can somehow iterate over this triangle and touch every single combination of t1 to get every single possible combination of t2, then we will have accomplished our mission of finding what the integral I2 is. So basically, all we need to do is to somehow evaluate f double prime of t2 at all the valid inputs in this triangle. Now we've been doing it by first changing t1 from a up to t0, and then changing t2 from that value of a up to the corresponding value of t1. Instead, we could do this. We could change t2 from a up to t0, and then while doing that, the corresponding values of t1 would be going from this line here, t1 equals t2, to the right here. We can see that would give us the equivalent sum. Here, for any value of t2, we stop and then we go from that corresponding value of t2 up to t0. So then, integrating from a to t0 and then integrating that value from a to t1 of something dt2 dt1, as in varying t1 first and then varying t2, would be identical to first varying t2 from 0 to t0, as in varying first from a to t0 our value dt2, and then while varying that value, then we vary t1 from the current value of t2 up to t0. So then vary the current from the current value of t2 up to t0 the value of t1. These two operations would be identical. Using this knowledge, we are going to be swapping this integration over here. So what we are going to do is use this knowledge. This is basically scratch work. We are going to cut it, and we are going to be using this knowledge here that we've just shown by observation, basically, that this integral is also equal to the same function f double prime of t2 evaluated as t1 changes from t2's current value up to t0 as t2 changes from a up to t0. So then these two expressions are identical. Here the first expression we are evaluating t1 first, and then as we change t1 we are changing t2 based on t1. In the second expression that we've converted here, first we are changing t2 and then we are changing the internal variable t1 based on what t2 does. Both of these operations are identical. Now then, erasing the scratch work, let's solve this integral. What we have is the integral of t1 changing from a to t0 of the integral of t1 changing from t2 to t0 of f double prime of t2. Since f double prime of t2 is a constant relative to t1, we can actually take it out of the first integral. Doing that, we have the integral from a to t0 as t2 changes of, taking this thing out as a constant, we have f double prime of t2 times the integral from t2 to t0 of dt1. So then we have this. Bringing this d2 a little closer, we can simplify it to this. So here what I've done basically is taken f double prime t2, which is independent of the value of t1, out of the integral, and then I have simply have just a 1 left in here. So we're integrating basically 1 dt1 here, and then this thing dt2. So now then, simplifying this, on the inside we have this integral which we can simplify over here. This is basically, this part basically is 1 integrated with respect to t1, as in it's t1 evaluated at t2 to t0. So we have the limits going from t2 up to t0, which is going to be equal to the value of t0 minus the value of t2. So basically this integral here, this definite integral on the inside here, is equal to t0 minus t2, which we are going to immediately replace. So then, cutting this scratch work once again, we are going to immediately replace this thing with t0 minus t2. So then what we have here is this is equal to the integral from a to t0 of f double prime of t2 times t0 minus t2 dt2. So now we have this integral expression over here. So then we're going to take this, we're going to simplify it a little bit, not simplify, rearrange it, and say this is equal to the integral from a to t0 of t0 minus t2 times the double integral, so double derivative of t2 integrated with respect to dt2. So now we have this. Now then, I'm going to take this and substitute that as I2's actual value and solve it. So then, writing this thing, we can say that I2 is equal to this integral over here. Now, at this point, what we are going to do is go up and bring equation number 3 into the picture. Equation number 3 states that the second derivative of f of t2, as in the second derivative of f evaluated at t2, is going to be equal to this expression here, which I'm going to copy and substitute in place of what we had down there. So down here, what we have is that I is equal to the integral from a up to t0 of t0 minus t2 multiplied by the double derivative of f evaluated at t2, which we can replace with our expression in equation number 3 as this. And then that whole thing then integrated dt2. So now we are going to have this integral here. This integral is integral number 2 or I2. Here we can see once again we have a sum of two terms here which we can break and evaluate separately. So we're going to do exactly that. Over here we're going to rewrite it one more time and then break it. Multiplying this t0 minus t2 into the 2, we have the integral from a to t0 of t0 minus t2 times f double prime of a plus t0 minus t2 times this integral from a to t2 of f triple prime of t3 dt3, and then all of this needs to then be evaluated dt2. Now then we are going to break this integral into two pieces and we're going to color code them once again and solve them separately. Here we are going to break this first part out and write this as the integral from a to t0 of t0 minus t2 times f double prime of a dt2. So here we have dt2 plus, and then this second part which is going to be the integral from a to t0 of t0 minus t2 times the integral from a to t2 of f triple prime t3 dt3 dt2. So this is the expression we have. We're going to color code this first one separately and the second one separately. The first one we color code in this blue here, this like cyan kind of blue, and the second integral we'll color code in we'll color code it black. Actually we'll color code it this dark green. And now here we are going to be calling this dark green integral as integral I3. So we're going to color code it and write it as integral I3. And this second integral here, this blue part, we are going to be simplifying because it is simplifiable. So then simplifying this thing down, here we have t0 minus t2 times f double prime of a. F double prime of a relative to t2 is a constant, so we can take it out, which means this is f double prime of a multiplied by the integral from a to t0 of t0 minus t2 dt2. Note here, this thing bears a resemblance to what we had earlier in lemma number 2. This is going to be our first instance of using lemma number 2. Lemma number 2 shows us that if we have this format p minus x dx, what we are going to have as our integral is u to the n plus 1 divided by n plus 1 evaluated from p minus a to p minus b. So in this case p is the value inside the integral here and a is this thing here, b is this thing here. So then using this thing we'll actually copy the result and we'll use it in this context. In this context, taking this down here, what we have is u being this part over here, t0 minus t2. Over here, since we have t0 minus t2 to the power of 1, n is going to be 1, which means we have u squared divided by 2 evaluated at p minus a and p minus b. So we have u squared divided by 2 evaluated from p minus a. In this case is going to be exactly actually t0 minus a. So here we have t0 minus a, and the second part p minus b is going to be t0 minus t0. So on the bottom we have t0 minus t0 as in 0. So then this is the integral that we are going to have in here. Simplifying this thing, what we have is u squared evaluated at t0 minus a and evaluated at 0, which is going to be t0 minus a squared over 2 minus t0 minus t0 is 0, so we have 0 squared over 2, which we can cut out and just write t0 minus a squared over 2. So this is this thing times t0 minus a squared over 2. And then plus the second part of this integral, which we are going to label now as I3 and move on to solve I3. We are only going to do one more of these cycles and then we are going to see the general pattern, and we are going to stop there and write this as a continuous sum. So then we'll do this one more time. Here what we are going to do first is we are going to simplify this I3 into a format where we are then going to be using the similar logic to what we did earlier. Recall that graph of the two and the input space that we need to be considering. We're going to be doing a similar logic over here. So we're going to take I3, and I3 over here, t0 minus t2 is a constant with respect to t3, which means we can actually take this inside of this integral. Doing such, what we have is the integral from a to t0 of the integral from a to t2 of t0 minus t2 times f triple prime of t3 dt3 dt2. What we're going to be doing here is swap these two. In order to do that, once again we're going to be considering what we're actually doing here. Writing this out in a grid, the possible values of inputs for t2 and t3, what we're actually doing here is this. Consider t2 to be on the x-axis like this and t3 to be on the y-axis like this. We're going to be needing the y equals x line as in the t3 equals t2 line, so I'll draw it preemptively. So what we're considering here is for t2, we're going to vary t2 between a and t0. So therefore t2 starts at a and ends at t0. So now then we have this. As we vary t2 like this, t1 is going to have to be varied between a and the current value of t2. So therefore it's going to have to vary between a and whatever the current value of t2 here is. So here if we consider this thing, drawing this thing, t2 is over here. If we consider at this point, t3 is going to have to vary between a and the current value of t2. At this point, t3 is going to have to vary between the current value of t3 and a, so like this. And then this has to continue until the final point where t2 reaches t0, at which point t3 would also have to be varying between between a and t0, because here t2 would be t0. So then once again the input space that we need to somehow cover here is this stuff here. For each of these inputs we need to evaluate t0 minus t2 times f triple prime of t3 and sum all of those values together. So then currently what we're doing to iterate over this input space is changing t2 from a up to t0 and then changing t3 from a up to the current value of t2. Instead what we could do is this. This level here is t0. Instead of varying t2 and then varying t3 based on t2, we could instead take t3, vary t3 from a up to this level here t0, and then while doing that, t2 would then have to vary from the current value of t3 up to the maximum limit, which is t0. So therefore, integrating from a to t0 and then integrating that from a to t2, dt3 dt2, integrating whatever is inside here in this format would be identical to integrating first t3, as in first we change t3, so t3 on the outside, t3 being changed from a up to t0, so t3 being changed from a up to t0, of then changing t2 dt2 from the value here, which is going to be the value of t3, up to here, which is going to be t0. So varying t2 from the current value of t3 up to t0 of whatever is on the inside. Using this, what we are going to be doing is changing up the order of integration on the integral I3 over here. We are going to instead write this as being equal to, in green, we are going to write this as being equal to the integral from a to t0 dt3 of the integral from t3's current value up to t0 dt2 of the function on the inside, which is t0 minus t2, so t0 minus t2 times f triple prime of t3, so f triple prime of t3. Now then here we can see f triple prime of t3 is a constant relative to t2, because no matter what t2 is, t3 is going to be t3. So here for these two, we can actually take f triple prime of t3 out of this first integral. Doing that, we get the integral from a to t0 dt3 of f triple prime of t3 times the integral from t3 to t0 of this thing on the inside here, which is t0 minus t2 dt2. Now then, once again we have reached this point. Here what we're going to do is use the formula we had once again, and here t0 minus t2 evaluated from t3 to t0 is going to be t0 minus t3 squared over 2. This time I'm not going to explain why we got it from the lemma. We're going to be directly substituting that into here. So then doing that, what we have is that this is equal to the integral from a to t0 of f triple prime of t3 multiplied by this integral, which is now this value over here, and the whole thing needs to be then integrated dt3. So now what we are going to be doing at this point is what we did previously, which is breaking this integral into two pieces using the formula for f triple prime of t3. So up there I didn't actually write the f triple prime of t3's value, but we're going to write it down here. F triple prime of t3 is going to be f triple prime evaluated at a plus the integral from a up to t3 of f4 prime of f quadruple prime, which I'm going to write as f4 over here at the top right to indicate that we have the fourth derivative of f evaluated at some variable which is going to be t4 to match the pattern, d that variable, so dt4. Substituting this into this expression here, we can now say that integral 3 is equal to, and then taking this whole thing, what we're then going to do is substitute f triple prime into here. So taking this thing, we're going to copy the whole thing, Control V, bring it here, and then we're going to take this expression down here and substitute it in the place of the top expression. So cutting all of this unnecessary stuff here, cutting f triple prime t3, we're going to be replacing f triple prime t3 with this whole expression here. So we're going to take it, Control X that part, we're going to put some square brackets so that it's contained, and write it in here. So here we have this whole thing here. We have a little bit of issue. I've actually accidentally taken one of these 2's along with me, and we also don't have enough space, so we're actually going to move this thing out of the way a little bit, take this whole thing again, Control Exit, and Control V it over into here, and put a bracket around it. So here, this is our expression. So now, once again, what we're going to do, I'm only going to do this one more time, at which point we'll see the pattern, and I'm not going to do it again. But here we can see, once again, we have an integral containing a constant part and another integral within it. You can see the pattern. We're going to have this thing which is now going to turn into another integral, which we're then going to have to solve in the same exact way using color coding and breaking this part in one, breaking the other part, solving the part with the constant separately. This part's going to get solved, and this other part is going to become another integral which is going to produce another integral. So then what we have here is the first integral, which is going to be this constant part's integral times this second part over here, which I'm going to write out as the integral from a to t0 of this part here, which is t0 minus t3 squared over 2 times f triple prime of a, so f triple prime of a integrated with respect to t3 plus the integral as t3 goes from a to t0 of this whole integral multiplied by this part here. So we're going to have the integral from a to t0 of that part t0 minus t3 by 2 this part squared times the integral from a to t3 of the fourth derivative of f evaluated at t4 dt4 dt3. You might see here what we're going to be doing is once again swapping these things order of integration. We're exactly going to be doing exactly that, but for now let's color code these into two integrals and solve them separately. Let's call this, let's say, the black integral, and let's take this part and call it the we don't really have that many colors left. Let's say this integral here, the gray integral. So we have the black integral and the gray integral. we're going to solve the bracket integral, and we're going to keep the gray integral and label it as integral number 4. So here we're going to have this part here being integral number 4. So then let's look at integral number 3 and what we're going to probably get once we solve integral number 4. So the black part that came from integral number 3, taking it, here we can see f triple prime of a is a constant relative to t3, so we can take it out. Taking that part out, we can see that this is equal to, and what we have here is equal to f triple prime of a multiplied by this integral here, which is the integral from a to t0 of t0 minus t3 squared by 2 and dt3, and then plus we have the additional plus i4. So now considering i3 over here, i3 is black part over here. Here we have something which we are familiar with. We have t0 minus t3 squared, and then there's an extra 1/2 here which I can actually take out, which I will do. I'll put the 1/2 over here and consider only this part on the inside of the integral here. So now considering this thing, this bears a resemblance to the form that we had in our lemma. We have some constant minus our value which is changing, which is t3 here to the power of n, which is 2 dt3. So now using our lemma, I'm not going to solve it, I'm not going to show you how we solve it, I'm directly going to write the answer. This is going to be f triple prime of a divided by 2 multiplied by, and this thing right here is going to evaluate into t0 minus t3 cubed over 3. You yourself can try using our lemma or by baseline baseline integration into try to find what this thing is. It is this exact value here. And then onto that, we need to then add another value of i4. So now here, I want you to notice that here we have 3 and we have 2, and if we had a 1, we would also have a 1, which means we can write this denominator as 3 factorial. In fact, we're going to do that. We're going to write this as f triple prime of a times t0 minus t3 cubed over 3 factorial plus I number 4. So here what I want to convince you of is that I number 4 is going to give us a similar part over here. To do that, what I'm going to do is rewrite i4, and I'm not going to solve i4 completely. I'm going to also skip the step of making that triangle and then showing you how we change the variables. Rather, I'm going to quickly show you that i4 is going to give us something that is very similar to this. So then, writing down i4, we can see that i4 is going to be equal to, going up here, I'm going to copy this thing that we had, this expression for i4, taking it, copying it down, we have Control C, Control V down here. So i4 is equal to this thing here. Here what I'm going to do is change the variables. First off, I'm going to take this into here. Since t4 is independent of this expression here, it's a constant, so we can take it inside without a problem, which means this integral is now going to be equal to the integral from a to t0 of the integral from a to t3 of t0 minus t3 squared over 2 times f fourth t4 integrated dt4 dt3. We can see the pattern here, and what I'm going to do here is immediately swap the two integrals. Writing this down here, what we have is equal to the integral from a to t0 of the integral going from t4 to t0 of this whole thing, which is t0 minus t3 squared over 2 times the fourth derivative of f t4 dt3 dt4. You can see this operation has been completed. We have swapped the two integrals, and accordingly, if you evaluate it out using like a piece of paper and try to figure out what the input space is, you can see that these are the correspondent limits. So now that we have this, we can see first we are evaluating with respect to t3. Since t4 is independent of t3, we can take this whole term of 4 derivative of f evaluated at t4 out of this first integral here and take only that integral separately. So here we have the integral from a to t0 times the fourth derivative of f evaluated at t4. I'm actually also going to take this half out completely as 1/2, and then here what we are going to have is the integral as we go from t4 to t0 of t0 minus t3 squared, the divide by 2 is outside so we don't need it, dt3, and then the whole thing dt4. So now then we can see with this first part over here, this thing is exactly what we had in lemma number 2. We used lemma number 2 to solve this exact expression, which is why I actually have lemma number 2 as a lemma. So here we can see we have t0 minus t3 squared, so here n is equal to 2. So then what we have here, this integral is going to be t0, as we found earlier from the pattern, is going to be t0 minus t4 cubed divided by 3. So then we can substitute that into here. The whole thing is to be integrated dt4. We have half, we have equal to integral from a to t0 of f's fourth derivative evaluated at t4 multiplied by this expression here, dt4. So now what we're going to do, once again, as we know the pattern by now, is we're going to take this f4 and we're going to substitute instead of it our expression containing the constant part f4 of a and our next part, which is an integral. So here using that, what we have here, f fourth as in the fourth derivative evaluated at t4 is going to be equal to the fourth derivative evaluated at a plus the integral from a to t4 of the fifth derivative, which is f5, evaluated at some variable t5 dt5. We are going to be substituting this into here. So then I'm going to cut this extra bit and we're going to be substituting instead of f4 this expression here. So then taking this thing, we're going to take it down here so we can substitute it later. Here what we have, we're going to copy this whole expression and substitute instead of f4 this part here. So we have, taking this down, we can make a little bit of space and substitute in. So then what we have here, deleting this term needs to be then be substituted by this term on the right here. So taking this stuff over here away, we have this whole term which needs to be substituted into here. It's too big, so I'm actually going to shrink it a little bit and put it in here. So we have this term in here, which is what we need. Deleting this x here because I don't need it and we don't need the multiplication sign here. We can close this into a square bracket and write this as our substitution. So now this is our new expression. This is our new expression. I'm going to change its color to color code it with the rest. This is what we need to evaluate. Once again, what we're going to be doing is breaking this integral into two pieces. You can see the pattern. By induction, what you can see is what we're going to have is, here I'm going to take this 1/3 over here and this 1/2 out over here separately. So we're going to have, if we take the 1/3 and the 1/2 out, we're going to have 1/6. Therefore we have over here 1/6 or 1 divided by 3 factorial multiplied by this whole thing. So here, splitting the two, this first part is f4th integral from a to t0 with respect to dt4 and multiplied by this whole part. So here we have the integral from a to t0 of t0 minus t4 cubed, and since we have the divide by 3, I actually don't need to raise this up because the divide by 3 is already outside as a divide by 3 factorial, multiplied by f fourth as in the fourth derivative of f evaluated at a dt4 plus the same exact thing 1 divided by 3 factorial times the integral of a to t0 of this integral here, which is the integral from a to t4 of f5 t5 dt5 times this part, which is t0 minus t4. Actually, since we removed the 3, we have that part also outside, so we have t0 minus t4 cubed dt4. So this is the expression that we have. Here once again I'm going to color code these. Since I've actually run out of colors, I'm going to reuse colors. This thing I'm going to color by the green integral, and this thing I'm going to color as the red integral. So now here, this red integral is what we actually want to label as integral number 5, I5. So we label this guy as I5 and we'll solve I4 and we'll end it there because that's actually enough for us to identify the pattern. So then, simplifying this, we can see for the green integral, this part is a constant relative to t4, which means we can take it out. So here what we have is f4a divided by 3 factorial times the integral from a to t0 of t0 minus t4 cubed dt4 plus, and then this rest of the integral is I5. So now then, taking the green integral down, we can see this right here is what we had in the lemma, which means we can take it out. Here we have f4a over 3 factorial, and we know from the lemma that this thing, as we saw previously, I'm not going to go into how we solve it because you can do that yourself. This is going to be t0 minus a to the 4th power over 4. So these two multiplied together plus the extra I5 over here. So now here I'm actually going to simplify the green part here by taking this 4 and the 3 factorial and writing that as divided by 4 factorial. And then here I'm going to take this part and write that as t0 minus a to the 4th power times f4 evaluated at a plus integral number 5. So we're actually going to end it there because we at this point can see the pattern that's going to happen here. So now let's rewrite everything that we have developed so far. We have developed that I4 is equal to this expression here. So we'll write that down. We have that I4 is equal to t0 minus a to the 4th power over 4 factorial times f 4th of a. We can continue by induction, but we're not going to do that. We're just going to look at the pattern and show that the pattern exists. Well, we could rigorously prove this by induction, but we're not going to. The next part here, I3, is going to be the third derivative of a evaluated at a times t0 minus a cubed over 3 factorial plus I4. Writing that down, we have I3 equal to t0 minus a cubed over 3 factorial f, I'm going to write instead of the 3 primes as 3, a plus I4, and I4 is this value over here. And then I2 similarly is going to be t0 minus a squared over 2 factorial times f2 of a. Instead of writing f double prime, I'm going to write f2 plus I3. And then what we had initially is that I1 was equal to t0 minus a times f1 of a, as in the first derivative, divided by 1, which is 1 factorial. So of course it's the same thing as writing just t0 minus a, but to establish the pattern we're going to show this. And then plus I2. Now then, for the last thing, what we're going to do is write our original expression for f at t0, which was t0 minus a to the 0th power, as in just 1, divide by 0 factorial, which is also 1. So this whole term is just 1, but to establish the pattern I'm going to write it. Also I'm going to say that the 0th derivative is the original function, in which case I can write that this is f superscript 0 in brackets of a plus I1. Now we can see the pattern. Merging all of these together, we can get that f evaluated at t0 is t0 minus a to the power of 0 over 0 factorial multiplied by f0 as in the original function, the 0 derivative as in the original function evaluated at a, plus I1, which is t0 minus a to the 1 over 1 factorial times f1 of a plus I2, which itself is going to be t0 minus a squared over 2 factorial times f2 of a plus I3, which itself is also going to be t0 minus a cubed divided by 3 factorial f third of a plus I4, which is itself going to be t0 minus a to the 4th power over 4 factorial, which we've proven, f fourth of a plus I5. We didn't go anywhere past I5, but we can see the pattern is going to continue. So then, if we continue like this up to some nth derivative and we stop there, we're going to have a pattern that looks like this. F evaluated at t0 is going to be the sum of terms from r equals 0 up to n of t0 minus a to the power of r divided by r factorial times f super r evaluated at a plus the very next derivative, the very next integral after that. Here, since we went up to 5, we have the fifth integral over here. We went up to the fourth derivative, which means we have the fifth integral. So if we go up to nth derivative, we're going to have the n plus 1th integral. So here we need to have I sub n plus 1. So here what we're going to have is the n plus 1th integral at the very end of the summation. What we are claiming by the Taylor series is that if this thing approaches 0 as n approaches infinity, then f evaluated at t0 is going to be exactly equal to this sum approaching infinity, which of course is true. If we take the limit of both sides as n approaches infinity, this side is going to be the exact same. So f t0 is going to be the limit as n approaches infinity of this whole thing, since this term converges to 0, which means that this is going to be equal to the limit as n approaches infinity of the sum as r goes from 0 up to n of t0 minus a to the power of r divided by r factorial times f r of a, i.e. we have our Taylor series expansion. Of course, provided that this term here approaches 0. This term right here is what we labeled in the beginning as r sub n of x. This is the term which we are going to call now the remainder. If this remainder, this additional integral that we have to evaluate, approaches 0 as n approaches infinity, then the Taylor series holds. It converges at that point. If not, the Taylor series does not hold, and in which case we cannot use it. So then, we need to show that this r sub n of x approaches 0, and we need to do that for each function that we need to find the Taylor series of, because of course different functions are different. Some functions it might converge to 0, some functions it might not. So now let's try to find a uniform format of this r sub n. We're going to actually end the video once we do that, and in future videos I'm going to prove different functions using the Taylor series and find different functions Taylor series. I gave a few in the start as examples, but we're going to prove a bunch of them, and we're going to prove them in the next video. So for now, we're going to find a common nice way to represent r sub n and end it there. So here, rewriting r sub n was this integral up here. If I copy this thing down, this thing right here, this is r sub n, so copying this down, we can write that r sub n of x, the value that we want to find, r sub n of x, the value that we want to be converging to 0 as we get larger and larger n's, is going to be this thing right here. Now here, there's a little change. Since what we're looking for is f at t0, I'm actually going to substitute this instead of r sub rx, I'm going to substitute r at t0. So this is the expression we want. We can simplify this a little bit in order to turn this into something that's closer to some expression using n. So then, looking at the integral on the right here, we have a double integral, which first thing what we're going to do is actually convert this into a single integral format. In order to do that, as you may recall, we need to swap the terms. So then, what we're doing here is integrating t5 from a to t4 while changing t4 from a to t0. So I don't need to go into this. We can draw this thing, and then we're going to get that this integral on the inside here, we have 1 divided by 3 factorial times the integral as t5 goes from a to t0 times the integral as t4 goes from t5's current value to t0 of the stuff on the inside, which was the fifth derivative evaluated at t5 times this thing right here, which is t0 minus t4 cubed. So this is what we need to find. So now then, we're going to rearrange this thing a little bit to get a nice thing. We're going to take this part out of this first internal integral. Because t5 is independent of t4, we can do this. So by doing this, we get 1 divided by 3 factorial times the integral from a to t0 of f fifth derivative evaluated at t5 times the integral from t5 up to t0 of this part here, which is going to be t0 minus t4 cubed dt4 whole thing dt5. We know what this internal part is. We know it because we've solved it previously. We have 1 divided by 3 factorial integral from a to t0 of f fifth t5, and then this part here we know it to be t0 minus t5 to the power of 4 divided by 4. So here what I'm going to do is actually take this 4 out as something like this. We're going to take this 4 out, and we're going to take this 4, merge it with this 1 divided by 3 factorial as a 1 divided by 4 factorial, and then here I'm going to leave on the inside the integral from a up to t0 of t0 minus t5 to the 4th power times f fifth evaluated at t5 dt5. Now then, we can see that this is I5 or r sub 4 of t0. So we can write this as r sub 4 of t0. Now then we can see, if we write this in a common way for n, in this case 4 is going to give us 1 divided by 4 factorial. This power is 4th. The symbol that we're going to use is the 5th. We have 5th derivative here. Writing this in a common form, we can see that r sub n of t0 must be 1 divided by n factorial times the integral from a to t0 of t0 minus, and in general here, since it doesn't matter what the symbol we're integrating with here is, I'm going to write just some random t to the nth power times the n plus 1th integral evaluated at t dt. So therefore this is the expression of the remainder, which means if we want to test if a Taylor series is convergent, we need to test this expression right here as n approaches infinity. So then we can write that this is the expression we need. So therefore, as a final summary, we'll write that f t0, the thing we wanted to find, is equal to the sum as r goes from 0 up to n of all the terms going as t0 minus a to the power of r divided by r factorial times the f's r derivative evaluated at that given value of a plus the extra term, which is going to be r sub n of t0, which is going to converge to 0 for certain functions. For the convergent function, so we could say like for the valid functions, this is going to converge to the Taylor series that we know, which is that f evaluated at t0 is going to be the sum as r goes from 0 to infinity of t0 minus a to the power of r divided by r factorial times the r derivative evaluated at a, since this term will be converging to 0 for those functions. That's all for this video. In the next video, we'll be doing this thing and proving this for certain special functions. So stay tuned for that. You can watch that. Probably I'll link it in the top right if I have made it. If I have not made it, you'll have to wait a little bit for me to make it. But that is the end of this video here. So that's the Taylor series. I hope you learned something. I hope you try different functions on your own. If not, if I have created a video, I'll link it in the top right. And that is it for this video. So thank you for watching and goodbye.